Past immersed bodies. Let us start the second part of the chapter, which is flow past immersed body. Basically, flow past immersed body describes that when a solid body is inside the fluid in moving condition, then what is the effect on that? And for that we have to study two important terms, drag and drag coefficient. So let us start with first term, which is known as drag. Basically, drag is the force in the direction of flow exerted by the fluid on the solid. That means when there is a solid in the path of the fluid which is moving, so the force in the direction of flow exerted by that fluid on that solid is called as drag. Fine. So this is the definition of a drag, force in the direction of flow exerted by the fluid on the solid. There are two types of the drags, form drag and skin friction drag. What is that? The sum of component of pressure forces in the direction of flow is called form drag. The sum of component of pressure forces in the direction of flow is called form drag, and it is due to shape of the body. It is reduced but cannot be zero. Obvious, because it is due to shape of the body. So we can reduce it, but we cannot make it zero. Clear what is form drag? It is the sum of component of pressure forces in the direction of flow is called form drag, and it is due to shape of the body. So we can reduce it, but we cannot make it to zero. What is skin friction drag? Skin friction drag arises from the friction of the fluid against the skin of the object that is moving through it. We all know what is skin friction. And due to that skin friction, the drag arises from the friction of the fluid against the skin of the object which is moving through it, is known as skin friction. And it is due to retarded boundary layer in contact with aircraft skin. Fine. So this is the basic meaning of drag. Two types of the drag, form drag and skin friction drag. Clear? Now let us see drag coefficient. What is drag coefficient? In fluid dynamics, the drag coefficient is a dimensionless quantity that is used to quantify the drag or resistance of an object in a fluid environment such as air or water. So drag coefficient is a dimensionless quantity and used to quantify the drag, or I can say resistance of an object in fluid environment such as air or water. It is used in the drag equation in which a lower drag coefficient indicates the object will have less hydrodynamic drag, and the drag coefficient is always associated with surface area. That means I can say that drag coefficient is associated with the shape of the object. That is also surface area. So drag coefficient is associated with the shape of the object. The drag coefficient of any object comprises the effect of two basic contributors to fluid dynamics: skin friction drag and form drag. Fine. So this is drag and drag coefficient. Drag coefficient is denoted by CD. C suffix D used for drag coefficient. And it is the equation of CD. That is drag coefficient. Drag coefficient CD is 2FD divided by rho U square A. Now what the term describes? CD is equals to 2FD upon rho U square A. Now what are the terms? FD is drag force that is force component in the direction of flow velocity, that is Fd. Rho is mass density of the fluid. U is flow speed of the object relative to the fluid, that is velocity. And A is reference area. So this is the equation which is used to calculate drag coefficient, and it is a dimensionless quantity. That means if you put the units of all these terms, the all units will be cancelled out, and that's why we call it as dimensionless quantity. CD is equals to 2FD upon rho U square A. This is the equation to calculate drag coefficient, and these are the terms which describes. Now let us see relation between drag coefficient and Reynolds number. Drag coefficient in general depends on Reynolds number, but also dependent on shape and orientation of particle with respect to flow. In general, drag coefficient depends only on Reynolds number, but it also depends on the shape and orientation of the particle. With respect to what? With respect to the flow. See, this is the graph of CD versus NRE. See here, this is CD, that means drag coefficient. This is NRE, that is our Reynolds number. You can see that there are different lines. You can see this one line is like this, another line is like this, another line is like this. The lines shows the different shape of the object. See, here written, this line is for sphere, this line is for cylinder, this line is for disc, this line is for sphere. That means I have already written that the drag coefficient depends on Reynolds number as well as the shape and orientation of the particle. That's why this CD versus NRE graph is different for different shape of the object. Fine. So when you know the value of Reynolds number and when you know the shape of the object, for example, the object is of sphere, the Reynolds number is here. Then what you have to do, from this line you have to extend to the sphere line and drag it to here, and you know the value of drag coefficient. Fine. So by this way we can use this graph to know the value of drag coefficient from Reynolds number. Now for low Reynolds number, drag force for a sphere conforms to a theoretical equation called Stokes law. For sphere we can use the Stokes law for low Reynolds number. Now what is Stokes law? For Stokes law, Fd is equals to 3 pi mu u0 dp, and CD is given by this equation. We have already seen that equation. CD is equal to 2Fd upon rho u square A, and Fd from Stokes equation is 3 pi mu u0 dp. Right. So now for low Reynolds number and for sphere particle, Fd is given by this equation 3 pi mu u0 dp, and we have the equation of drag coefficient CD, which is equals to 2Fd upon rho u square A. So now we want the relation between CD and NRE. How we can get? See both the equation. From equation number 1, put the value of Fd in equation number 2. From equation 1, put the value of Fd in equation 2 and simplify it. Then you put that and simplify it, you get CD is equals to 24 by NRE. That means you will get 24 upon du rho by mu. And what is that? Du rho by mu is NRE. So when you put the value of Fd from equation 1 in the second equation of CD, and when you simplify it, you will get this equation. CD is equals to 24 by NRE. So this equation represents the relation between drag coefficient and Reynolds number. Fine. So this is the relation between Reynolds number and drag coefficient mathematically. But if you want the graphical relation, then I show you that graph. If you want to calculate analytically drag coefficient, you have to use this equation. If you want to know the value of drag coefficient graphically, at that time you have to use that graph of CD versus NI. So this is all about the flow past immersed body. For flow past immersed body, the important parameters are drag and drag coefficient. And drag coefficient is related to Reynolds number. And we have seen that relation between drag coefficient and Reynolds number. Fine. So this is all about the second part of our chapter, that is flow past immersed body. In flow past immersed body, there are two parameters, drag and drag coefficient. So I am completing my lecture here. I hope this is clear to all. Thank you.